Hi, welcome back to PR Tech Talk. In this episode we're going to look into a similar project as I did in my last video, but it will be with a tweak. So I will looking into multi-channel DMA once more, but using DMA this time instead of IRQ. And I will also put another twist on it. I will trigger the DMA from a timer channel, so just to see that that is possible and how that is done. And I will also convert the internal temp sensors to degrees Celsius if you're curious about how that is done, and also for looking into the VBAT and the internal voltage that you can measure from the ADC within the G071. So take along. So we have this STM32 cube up, and we start by making a new project. File, new STM32 project, as we do many times before. I will be using the Nucleo G071 board, so I start with tagging the board selector and hit it in the commercial part number. I find it there, I select it and just next. Now we need to give it a name. So I call it Multi ADC DMA. Initialize all peripherals as default. We start by taking a look in the system core, and under sys just making sure that the serial wire is there, and then we can go to the RCC and deselect. I don't want to have these, so I just deselect the external crystals. I'm using the internal high-speed internal RC on 16 MHz, and so 16 MHz is good enough for me. And 16 MHz will also be the clock to the ADC, and 16 MHz will also be to the timer, which is driven from the APB clock. So nothing to do there, so we can minimize the system core and immediately go over to the analog part, and we select the ADC1. I will be looking into 4 channels this time. I will look into one external channel, and that is on ADC1, PA1, or PA0. So that is the IN0 there. And I will also measure the temperature sensor. There is an internal temperature sensor, and there is a voltage reference that we can also take out and have just for curiosity to look into that one. And there is also a VBAT channel, and the VBAT channel is if you have a backup battery that you would like to monitor. So that is available, and in this application it's, as we can see in this slide, it's connected to the VDD, so it should be the same as the VDD, and that is 3.3 volts. But we will take a look at that one as well. Then I'm just giving me some more space here, and we go under parameter settings. And we see here the synchronous clock divided by 2. We have a clock on 16 MHz divided by 2, that makes 8 MHz. We keep the ADC on 12 channel or 12-bit resolution and right alignment. And we go down here to the number of conversions. And we have now 4 channels that we would like to measure. So we changed that one to 4. And we also then have the scan conversion mode. We enable that one. That means that when we launch a scan or ADC conversion, we will launch all 4. So we will take them one by one and source the information to us. We also have the internal the clock for the temperature sensor that needs some timing, and that if you look into the data sheets and count it out, you will come to the 79.5 cycles that is needed. The rest I'm just keeping on 12.5 cycles. or we can even take 19.5, give them some more headroom. But then, as I said in my last video, now we come down to the very crucial part. We have told the ADC that he would like to convert 4 conversions when we started. But it doesn't know what to convert, so this is under the rank. So we open the rank, now we have 4 ranks. So the first rank 1, that is the channel 0, and that will be an external voltage that we would like to measure. And it asks us which sampling time this need. And in this time it's the common 2, so I will change that to common 2. The next one, they need to be changing that one, and that is the internal temperature sensor, and that requires some more cycles. So that is the reason for me having 79.5 cycles up here. So the internal timer, internal temperature sensor need that. So we put sampling time common 1 on that one. And the third one, we will have the voltage reference internal. We can give it the shorter sampling time, so we can have it with 2, and that means then 19.5 cycles. And finally the last one, that's the VBAT, and we also give it the 19.5 cycles to have the calculation there. This is what we need to do in this folder. Then we need to look into the DMA settings. And we need to add a DMA, and to what? We need to add an ADC1. And here we have, I just put full words, so it's 32-bit, and keep it as normal. That is what we need to do in the DMA, and now we also need to go into, we're coming back to this ADC once more after we have been on the timer. So we will launch the timer 2, and the timer 2 I will use, so I will start the timer 2 and I will put it on with the prescaler and counter to 1 Hz to trigger the ADC. So we can see that whenever this times out and gives an event, the ADC will listen to that one and then make the measurements for us. So we take on this one, and the first thing you need to know is what clock you want to feed to this, and it's an internal clock. It's in 16 megahertz, and I would like to come down to 1 hertz, so I take 16,000 in the prescaler. And if you recall my last video, if you have 0 in the prescaler, then you scale it by division by 1. So you need to actually put 1599, but it's odd, so I just make 16,000 minus 1 to recall that. And the counter period then we need to have on 1000 minus 1. Great, and then what will happen when this times out? We will enable some trigger, so it will trigger something. And we will have an event update. So whenever there is a timeout on this one on 1 Hz, it will have an event update. And what we can then go back to the ADC and parameter settings. And then we can take the external triggers conversion source. What should trigger this? And we should have the timer 2 trigger out event. So we click that one. And we can also make change here is end of conversion selection. We can have when the sequence of conversion is done. That is what we need to do here. I don't think that I forgot anything. So we build a project. Now the skeleton is done for us. I'm just trying to build it and see so there is no errors or any warnings. And as expected, there was nothing there. Now we need to add some code into this one. So to start, we take 2 variables and we put it under user code begin PV, and that stands for private variables. So we begin between the begin and the end. So I take a 32-bit and give it an ADC buffer and the ADC buffer size. And I also make another variable called uint8, a small one, for ADC ready, and I initialize that with value 0. And we also need to make a define up here. Define there. So we define ADC buffer size to 20, and it's not needed to have 20, but we will take that anyway. So this means that the ADC buffer will be initialized with a size of 20. Great, so now we go down to user begin 2. After all initialization is done, you have the whole initialization and the system clock and so forth and so forth. And we go down here to the user begin 2. There we need to start a couple of things. The first thing is actually not needed, but I do it anyhow. So I will put in this calibration. It's not needed, you can do without it, but it's just one line. Just copy it in if you have room enough in your application. It will calibrate the ADC with the factory parameters to you. And then we have the next line is the HAL ADC start with the DMA, and it takes 3 parameters. The first is the handler for the DMA channel, and that is the HADC1. And then the next one is where to put the information, and that is the ADC buffer, which we did up there. And then the ADC buffer size, that means how many should we actually do, and that was 20. We defined that from the very beginning. So that is how we start the ADC, and after that we also start the timer. And it takes 1 parameter, and that is the handler for the timer, and that is the STM32. We started the timer 2. So here we have the user code begin 4, and the defines for the callbacks are already defined for us, so we just need to know where to find it. So we can go down under drivers and the STM32G0 HAL drivers, and under the source you see all the HAL drivers that are available for us. And when we're talking about the HAL ADC, we open this one. So we have the HAL ADC open there, and here we have all the functions that are in this file. So we look now for the callbacks here. And we look here, something here, there. Whole ADC complete callback, and that is already declared for us as weak. And it says here also, this function should not be modified. When callback is needed, the function whole ADC completed must be implemented in the user file. So we copy this one, everything except the weak. And we paste it in under this begin 4. So whenever the buffer is full, we will have a launch of this callback here. In this callback, we will do 2 things. We will put a flag, EDC ready, and we will give that a value 1. So that is a flag that we will use later on to see that when we are done with the ADCs. And we will also stop the ADCs, otherwise it will be keep running. So we will stop the ADC as well. So HAL ADC stop DMA, and the handler is for ADC1. We tried to compile this one to see if we made any errors. Great, so far so good. What we now can do is go up to the main one and the while one loop. If we find it again here. So here we have the while one loop, and we just give us some room there. So here we have the while one loop, and I just made some small code here, and I said while ADC ready is not equal to 1, that it means that as long as it's 0, it will just remain here. It won't happen. It will just stop here and wait. And as soon as it's 1, that means when we had a callback from the function below that we just did and under the begin for, we will pass this and come to the next segment, and then I will immediately just put it to 0 again. So it will come up and stop here again, and we will add on this code later on. But just to take this first step, and we debug it. First time as you debug, you will get this information, and you hit the debugger. And I normally do like this. I just scan to see if there is a serial number, and that means that it can find a debugger. Now I try to communicate with the demo board and ask us if you want to change to the debug perspective, and you have the perspectives up here, and I would like to have this, but I just hit remember my decision, so it doesn't ask me more than this time. So now we need to do something to see what's happening here. So we will put some live expressions here. So we add expressions. So we took the ADC buffer and we expand that one. Now we see that we have 20 values because we had we said that we should have 20 places in our buffer, so that we have 20 places here. So what we now can do is run code. Now you can see with the 1 second interval you have this populated, and now it's stopped because everything is now done. We have made 5 times 4 conversions. And we can just relaunch it. If we suspend the code there, you have one reset. So if you just want to start from the very beginning, this is the tab that you click on there, and you also see that the live expressions went to 0 everything here. And if we just run it again, we can see now first 4, and then 4, and then 4, 4, and 4. So this is just to indicate that the timer is actually triggering all 4, and when it's triggered, we convert all 4 channels as we instructed it to do. We actually don't need all this data, we only need 4. So we can stop this and go back to the code again. And we can define our ADC buffer size to 4 instead. And we can do the same just for 2. Each time we go back, we need to just click on the live expressions. I'm not sure why it's done, but it's like this. So just hit the live expressions. Now we can see we only have 4 positions. So if we run again, you see that we will immediately just get this information here. So when this is now, the timer doesn't do anything because we triggered it, and then it's immediately populated the 4, and then it waits, and then it tried to trigger us again, but we're already done. And we stopped the ADC as well in the callback function, if you recall that. It says down here, let's see, where do we have it? Yeah. So when we have the callback, we stop the ADC. So the timer can try to start as much as it wants. It won't happen anything. So now the timer doesn't do anything for us. But that was just to show that you can actually use the timer to trigger ADCs. Great. So now we have these values here. And just to make sure what the values are for something, I have in my scopy, that is for the channel 0, so that is the value, the counts for the voltage here, and if we now change something, it won't happen. make any changes because this is static. We are not running any code right now, so it won't happen anything. But the other values, the buffer 1 was the internal temperature sensor, and 931, that is not the temperature I have, so we need to find out how we can make that to degrees Celsius. And the third one was the voltage reference internal, and that is not anything like what we have in voltage reference internal either, so we need to convert that. And the last one is the VBAT, and that is also incorrect. So this is counts, but we can't actually use this information too very much. But we will do that now. So we break this one and go back to the code again. So now I have gone down to the while one loop, and just beneath what we did earlier, we did the ADC ready 0, and beneath that now I had added this piece of code here. What this does is that we have a function within the tool called HAL ADC calc data to voltage. If we highlight that one, we can find where it's coming from. So it's coming from the STM32G0XX HAL ADC.H. So if you go down here, you can see that this is a helper, and it says here it helps to calculate the analog voltage for you. And I explained that in my previous video as well. So what we do now, we take the channel 0 millivolt, and I will declare these 3 variables, or 4 variables also, that is needed. And now let's see what happened here. Like so. So we have the HAL ADC calc data to voltage, and we take the VREF analog voltage, and we need to declare that one. And so that is the first parameter this function will take, and that is the VREF analog voltage. And the next one is the ADC buffer, and that is the data to where we had the DMA automatically fill in this information for us. So we don't need to gather the information that we did in the interrupt. So when all the interrupts were done, we need to get the information from the ADC to what variable. And this time the DMA puts it in where we actually want it from the very beginning. And we also need to know what resolution we have, and it's a 12-bit register. So this is the thing there, and then we have the next one, that is the internal temperature sensor. So that is a different one. So that is __ HAL ADC calculate temperature, and it also takes the voltage reference and what position in the voltage buffer, that is the second position, and it's also 12-bit. So we need to declare this reference voltage. So we go up here under our PD defines, and we define __ VREF analog _ voltage __. So there are 2 underscores in the beginning and 2 underscores in the end, and in the middle there is 1. It's hard to see, so that is why I'm telling you. And 3300 because we have 3.3 volts, so this is calculated in millivolts. Then we need to also make some variables for us. So I make all 32 bits. I have plenty of RAM, so you should actually be able to do it with 16 bits, since we only have 12-bit register here. But the first value is the channel 0 millivolt, and the second is the voltage reference internal in millivolt, and the third one is the VBAT millivolt, and the internal temperature sensor. Great, so we tried to build this code, and there was no problem with that, and we debug it. We go on the live expressions again, and we see that we have the 4 positions of the buffer, but that is not the main interest for us. We would like to have the new one. So So we add the channel 0 millivolt, and that was the first variable we put there, and the second one was vref internal millivolt, and we have the vbat, and we have the internal temperature sensor. So we have the millivolt, we have the vref, and we have the vbat and internal temperature sensor. And there was one thing that I forgot to mention. I will just run the code here, and I will tell you afterwards. So we run the code. So immediately we can see that now we have live data, and the reason for it is whenever we did this loop and we were waiting for the ADC to be converted, we were staying there. But as soon as the data was ready for us, we made all these conversions, and then I start the ADC again. And we can now see that if I take, for instance, this one, we see here that channel 0 is now, we can hide that one. And where is my scopy? There. So the channel 0 millivolt, that is the voltage which I'm sourcing from this source here, and it says 2.9. So now this is in millivolts. So 2900 something millivolts, and that is correct according to this one. So if we change this one now, we see now I have 9.2, and there is 9.2, 1.92 there as well. So it's actually real live data here. And if I'd like to put 3 volts, that is 3.02 measured, and that is 3.0. So it's quite good actually. The other thing is the vref internal in multi millivolts, that is 1200. So that means 1.2 volts. And if we take a look on this slide here, that is from the reference manual, we see that it should be, depending on the temperature around, it should be something like 1.2 volts. So that is correct as well. The vbat though, this is a bit tricky. If we take a look in the vbat, I did something special with that one. I multiplied the value by 3. And why did I do that? The reason for it we can see in this slide. So we take actually the vbat and have a voltage divider. So we take down the voltage on the vbat to be measured by 3. So we need to multiply that by 3 to get it correct. And lately and lastly, we have the internal temperature sensor, and it says 25 degrees. And if I now put my finger on it, it should be increasing. It does. And I still have my finger on it. So yeah, 30 degrees. So this is the internal temperature sensor of the die. So it's not to be measured or anything else, but mainly like to see how hot it's on the main board. So this concludes this demo, and I hope that you liked it. And if there is some uncertainty, give me some information in the chat, and I will answer as good as I can. You can also take a look in my previous video, because there was perhaps some answer to some of the questions that you had, and that was the ADC multi-channel with interrupt. But I hope that you learned something, and I earned that you give a thumbs up. I really like that. And if you're not a subscriber, please do subscribe and hit that round bell or the round circle beneath me, and then you will be a subscriber. So until I see you next time, stay safe.